years from our research on quantitative information flow, which started with the collaboration, thanks to collaboration with the Prakash, which started in 2005. Prakash visited us at RIX and showed him the research I was doing in trying to formalize in terms of probabilistic terms the concept of quantitative information flow. Prakash said, go information theory, which indeed was a very good idea, because everybody moved to information theory but at the same time, so we were among the first. And I should mention that this collaboration was also provided also the main material for the Costas thesis, which is Costas, the good thesis was also thanks to the fact that Costas is brilliant, but also thanks to Prakash who provided good ideas. So now I'm sorry I didn't think of bringing a gift for you, but I promise when I go home I'll send you a copy of Costas' thesis. And the other topic of this talk is the Kantorovich metric, which also derives from the seminal work of Prakash and his colleagues, Charnay, Chagadiza and Gupta, Concours 99, I think, in 2002, were the first works, and then of course also inspired by the works that Kantorovich did. But I remember I was at that time also struggling with the same kind of problem, also defining a more generalization of a simulation for probabilistic processes, and nothing worked. I couldn't get the right metrics, and then we saw your work. That's the way. And then also thanks to the fact that Prakash explained to me patiently how the Kantorovich metric works, and what it means, and so on. At the beginning, it was really strange to me. So, plan of the talk very quickly. I will actually start with the differential privacy, because for us that was the main motivation of studying this multiplicative version of the Kantorovich matrix. I will briefly introduce the notion of differential privacy and its motivation, for those who don't know yet. And generalize the version that we have developed, Costas and I. And finally, I will speak about the problem of verifying differential privacy in processes, and how this multiplicative variant of Kantorovich metric can help in that. So, what's differential privacy? Well, first of all, why it was proposed? Well, it was proposed in the context, in the area of, in the community of statistical databases, and essentially as a solution to the problem of using statistical databases, which means ask queries about aggregated information, without trying to preserve the privacy of the participants in the database, so trying to not reveal too much about their secret information, their private information. However, the problem is not so easy, because even if you anonymize the data, the fact that you derive some public information, some aggregated information, combined with the side knowledge or a priori knowledge that the adversary might have, might tell a lot about the private information of a particular individual. So, for instance, consider this database here, which is a medical database, which should serve to trying to derive, for instance, the correlation between a certain disease and the end. So, in principle, a query like what's the average age of the people who have this disease, or what's the minimum age of the people who have this disease, should not be dangerous for the privacy, in the sense that, in principle, shouldn't say anything about whether a certain person has the disease or not. But in practice, if you allow the adversary to know something extra than the query, like, for instance, the age of the people, or certain people, Then the answer, in this case, the answer to the query, what's the minimum age of a person who has the disease, could be, for instance, 40, and the adversary might happen to know that Don is the only person of age 40 in the database. So immediately the adversary knows that Don is the disease, which is not, in general, people are not very happy if it is found out. So what's the solution? So the first solution that was proposed, the most successful solution that was proposed to this problem before the advent of differential privacy was the so-called decay anonymity, that essentially is based on the idea of making sure that whatever answer you get from the database, there is always a group of people of minimum cardinality k that could have originated that answer. So in this case, for instance, we should make sure, if we wanted to anonymity, we should make sure that there is at least another person, say Carl, which has age 40 in the database, and so the answer, the person with age 40 of the disease doesn't allow the adversary to infer that Don has the disease. However, what's the problem? Well, let me say that this is a very simple idea, and considered also very powerful, and to the point that a lot of services that we commonly use, whenever, like for instance, Facebook, whenever they ask, when people started to be worried about the privacy in Facebook, the answer of the CIO was, well, don't worry, we anonymize everything. And the idea essentially is, since everything is anonymized on Facebook, the information that you can derive, I'm not speaking of course of the friends can derive a lot of information, the other people, in principle, cannot associate certain information to a certain person. But in fact, this kind of protection is very weak with respect to composition attacks. Let me explain briefly what it is. Composition attack is when the adversary can derive information also from another database. Okay? So now suppose that you have another database here that this time tells the correlation between weight and disease. And let's assume for simplicity that it contains exactly the same people. In general, it's not important. The universe needs to be the same. Necessarily the database. Anyway, suppose that also this database is too anonymous, so in the sense that there are always at least two people with the same weight. However, if you ask again the question, ask now the question of the kind of what's the minimum weight of the person who has the disease, well, in this case it would be 100. And now combine with the other one, the other answer, you see that you can see that there is only one person that is both pink and blue, so it's purple, and this is Don again. So in other words, if the adversary knows that the only person who has age 40 and weight 100 kilos is Don, then Don is Don is in trouble again. Okay. Okay. So that's the main property that the differential privacy is trying to provide: robustness with respect to compositionality. And what's the idea? Well, first of all, we start with the simple remark that if we remain in the deterministic realm, we cannot solve this problem, because you can always have enough intersection of sets to get to the singleton that originates the answer. So the only way to go to solve this problem is to use randomization. Randomization means essentially that we add noise to the answer, to the query, in a clever way, because also we add too much noise, then the database is not useful anymore. So we have to add a little bit of noise, so to make sure that we never rule out any possibility. So in a sense, we spread the probability of obtaining a certain answer over all the database in a way that, of course, the real answer gets more probability and the others get less probability. The more far away they are from the real answer and the less probability we get. That's in order to give some utility. But in this way, what we get is that even if we combine queries, we never throw away any possibilities in a sense. We, of course, we restrict the probability more and more, and this, of course, means that the adversary gets more and more knowledge, but in a sense it's controlled, right? So if we combine the answer here, for instance, you can see that everybody gets a little bit of purple. Dawn is more purple than the others, but not everybody's purple. Now, this question. So, typically, the way to do this is via a mechanism which is based on, so we add the noise in order to preserve utility, we have to add the noise in a clever way, namely, the probability should be higher for the real answer and then decrease as the answer gets more far away from the real one. One of the best mechanisms to do this is the one based on Laplacian noise, which is essentially a randomized function where the probability distribution of the noise follows this exponential curve, which well, we explain that y here is the real answer, z is the reported answer after we have the noise. So it's a negative exponential, which means the more far away the reported answer is from the real answer, the less probability we get. And then we have to make sure that we factorize it with respect to what we call a sensitivity of a function, which essentially, defined in this way, is how much difference we can get in the answer in databases which are adjacent to each other, where adjacent means that they differ only for one individual. Okay. So how much difference an individual can make in the answer. And of course, the more difference it can make, the biggest is the sensitivity of the function and the more noise we need to add. And for CC is just a normalization factor to make sure that this is probability distribution. So, finally, let me get to the concept of differential privacy. So, differential privacy is essentially just a way to formalize a notion of privacy and to ensure that that certain properties are preserved. So, first of all, one is that we want to add the noise in such a way, as already explained, that the utility of the database is preserved. The other properties are compositionality, which I already explained, and another important property is independence from the knowledge of the attacker. In other words, the a priori probability that the attacker has, the a priori knowledge that the attacker has anyway about the values of the individuals, independently from the answer that he gets from the database. So this is important because in general we want to design a mechanism which works for all adversaries. We don't want to change the mechanism depending on which adversary we get. Okay, so differential privacy tries to cope to provide a notion that has all these properties, and the definition of such property, as what we call differential privacy, was devised by Work and some colleague of Hertz. And essentially it's this, it's very simple. It says that if whenever we have two adjacent databases, and for every possible answer z to the query, okay, the probability that we get a z does not change significantly between x, having x or x prime. So if we change the value of an individual, the answer we get the same answer with almost the same probability. And this almost is quantified by this factor e to the power of epsilon. And epsilon is of course a parameter of this property. The bigger it is, the less privacy we have. Just to give a very quickly an idea of what this really means, this is an alternative and equivalent characterization. Now, the notation is a bit complicated, but let me explain what it means. Essentially, it means, differential privacy means that for every individual in the database, and for every possible answer that I can get when I ask the query, if I know the value of all the other individuals in the database, then the a priori knowledge, the a posteriori probability that the individual has a certain value does not differ too much from the a priori probability. So in other words, the adversary doesn't learn too much from the answer to the query. This fact that the adversary knows also the value of the other people in the database is not an advantage. I will leave that to you. I mean, it does not make the notion stronger. But I leave it to you to figure out why. Now, generalization, this is what we have proposed. So we wanted actually to see if this notion could be transferred to other domains other than databases, essentially because we were interested in location privacy. And we found out that there is a rather immediate generalization that we can do, so to make it applicable to other domains. And this is by looking at an equivalent version of the definition of differential privacy, which is this one. It essentially says that if we don't have, if two databases are not adjacent, I can still say something between about the conditional probability to generate a certain answer. What I can say is that the two probabilities, the ratio between the two probabilities, is bounded by the distance, the Hamming distance between the two databases. And you can see that it's very, very easy to show that this property is equivalent to the other. Hamming distance is the distance between, is the minimum path between the two databases. If I look at them as databases as a graph where the adjacency relation represent the edges. So we simply extended this by considering an arbitrary domain instead of databases, and replacing the distance, the Hamming distance with the generic distance of the domain. And then we played a bit with this notion, and we found out that, for instance, in this domain where we were interested in location privacy, this gives us a very reasonable notion of privacy, at least for certain application. Namely, the application we have in mind is location-based services. So when, for instance, you ask for restaurants near the area where you are, and you don't want to reveal the exact location, but you are okay with revealing the approximate location, namely the fact that you are in Paris instead of London. Okay, so in this case, we can, by applying this extended notion of differential privacy, which you can interpret as this one, essentially the fact that how much we can distinguish two locations a posteriori after we send the approximate location, does not differ too much by how much we can distinguish two locations a priori. So this is equivalent to the notion, we call it this notion general distinguishability, and is equivalent to the notion of differential, generalized differential privacy. And we can obtain this property by applying an extension of the Laplacian, essentially a planar, well, it's a particular extension that is given by rotation. It's not, the more common extension is the one, it's also called the bivariate Laplacian, but it is the one that projects along the two axes, but that wouldn't provide the differential privacy. The one, in order to get a differential privacy, we need just to take the rotative symmetry, how to call it anyway, you rotate, the normal Laplacian, and to get this one. Finally, 5 minutes, okay. Finally, let me come to the multiplicative version of the Kantorovich metric. So what we wanted to do with this was to extend this notion of privacy to processes, because we were interested, for instance, in figuring out what additional information you can get when you have also concurrency and so on. We formalize the notion of, if we have two probabilistic processes obtained from the same system by changing secret input, say here u and u prime, different values of the secret inputs, and we consider the two probabilistic processes that we obtain in this way. Now we can define a differential privacy as the property that for every observable A, the probability to do this A can be an action, for instance. The probability of A in the system with the secret U should not be too different from the probability of A in the system with the secret U prime. Where this not too different is depends on the distance between U and U prime. And this again is a parameter of the definition. It depends on the domain in which the secret. So, how to verify this property? We thought that we could use, we could try to change the notion of Kantorovich distance, which is what Frank spoke this morning about. So that notion would not have any relation with differential privacy, and in order to change it so that we could say something about the differential privacy, we figured that we could, so if you take the standard definition of the Kantorovich metric, the discrete version, is this one, where the xi are the Lipschitz function, is the Lipschitz function, is a variable of the problem. The mu and mu prime are the distributions on states, and m is the distance. So what you want to do, well, the step of the construction of the probabilistic the simulation metric is that every time you have a metric on the states, you derive another metric on the states by solving this linear, this problem, this linear optimization problem. And then there is this dual, which is this famous theorem, which saying that this problem here is completely equivalent to the mass transportation problem. And I think that, I'm not an expert, but I think that this second version is the one which is actually used for computing the metric. So we tried to make a variant, multiplicative variant that would be related to differential privacy by taking instead of the difference between the expected value of x in maximize the ratio. Subject to the constraint that, well, essentially the logarithm of this function is ELM Lipschitz. So in other words, okay, forget about that. The ratio between the value of the function on I and on j is smaller than A at the power of the distance between I and j. Okay, sorry. Then the nice thing about this formulation is that it's related to differential privacy, as I will show in a moment. And also, fortunately, we were able to find out that this problem here, which is not a linear optimization problem, can be reduced to an equivalent linear optimization problem, which then has a dual form of this kind, which we can use, which is now a linear optimization problem, and we can use to solve, to compute the new metric. So if we do the construction exactly like in the standard case, but replacing this step with the multiplicative variant, we get a metric, well, so there is a greatest fixed point to this transformation. We get a metric that is related to the differential privacy in the sense that, if the two initial states of the automaton are smaller than the distance between the secret, and so is smaller than the distance between the secrets, then the automaton is differentially private in the sense of some slides ago. And the other nice thing is that also this one is by simulation metric in the sense that it's zero if, and actually it's an if and only if. If and only if the two automata, well, the two states are by simulation of this sense. Yeah, sorry.
Exactly one real question.
I just want to say actually I've been very inspired by your work in this area, and I have a new graduate student who we're about to embark on studying differential privacy in that. So we look forward to reading the paper.
Okay. So we should produce it soon.
Yes.
So Jordan,
So at some point in the database application, you had a line about this approach is robust against repeated or compositional queries, and I'm just wondering how this works. I mean, if you were to you make the query to the database and out comes back the answer, which has been randomized. Suppose you were to repeat this query say 1,000 times, and you collect the times, and you could probably estimate with very high accuracy what the real answer is right now.
So composition is bad also for differential privacy.
Yeah.
And I only meant to say that it's controlled, and the way in which the privacy decreases can be calculated.
Yes.
Is always smooth, in the sense smooth. It doesn't decrease. Privacy does not disappear out of the sudden, like in the case of. So
Yes.
in the case of k-anonymity, you can ruin privacy completely.
Right, but with churn-off bounds, you can probably get very, quickly.
Yeah,
Right?
this
So,
is worked by the guy from Florence, what's his name, but Michele Boreale invented.
yeah. Okay.
all right, we're only 2 minutes late, which is as good as a Greek person can do. Let's thank